Avital Shurki from Hadassah Medical School. Avital, she is a scientific daughter of Ari Warshaw, as well, frequently talking about scientific children and grandchildren here. So unfortunately, he was not able to make it here, but we have a excellent speaker, Avital, right here. She did her PhD in Hebrew University in quantum chemistry, and postdoc with Ari, and she has her own lab from 2003. So please, Avital.
Is it working? Yes. I first want to thank the organizing committee, Julia, Nir, and Roger for inviting me. And okay, so I've been asked to give a very, very long introduction, and this is what I'm going to do, so be patient. And I will start by explaining what is QMMM, and then try to show you how can we use it in order to understand enzymes. Okay, so so in computational chemistry in general, I think we can divide it into two different disciplines. There is the molecular mechanics, which we've heard about this meeting, where we use classical theory. We relate to the particles as particles. We can use and calculate large molecules because it's a relatively cheap method. The problem with that method is that it cannot calculate reactivity. We cannot use molecular mechanics in order to calculate reactivity. On the other hand, there is molecular mechanics. So molecular mechanics uses quantum theory. Here we consider not only the atoms, but we really go into the details. We calculate the electrons, we calculate the wave functions, the orbitals, where the electrons are. So using that theory, we can actually calculate many, many properties. However, there is a disadvantage, and that is because it's such a detailed method, we can calculate only relatively small molecules. So the advantage, however, is that we can actually calculate reactivity, we can calculate various spectra, etc. Quantum mechanics is divided into various methods. We have valence bond, we have molecular orbital, and we have density functional. These are all different methods within the quantum mechanics approach. So just to give you some small insight, if we want to consider the F2 molecule, just an F2 molecule, so in molecular mechanics we will consider this molecule as two balls with a bond between them, and that's it. Whereas if we consider it in quantum mechanics, so we have two nuclei with 18 electrons and 9 orbitals if we consider a molecular orbital picture. And these 9 orbitals are going to be usually described by many, many more basis functions. So you can see the difference between these two approaches. That's why this one is much more expensive, computationally expensive. However, what happens if we want to calculate reactivity, but within a large system, for example, within a protein? So for that, we cannot use only quantum mechanics because it's too big. On the other, and we do have to consider the effect of the protein on the reaction. On the other hand, as we said, molecular mechanics cannot calculate reactivity because we have either a bond or we don't have a bond. There's no such thing like a partial bond in molecular mechanics. And that's where comes the combination of QM with MM. So what is QMMM? If this is my system, our system, so we divide the system into the reactive part where the reaction takes place, and the rest of the system, which we will refer to as the environment. So what we do is we calculate in just a minute. We calculate the reactive part using quantum mechanics, and we calculate the environment, the rest of the system, using molecular mechanics. Now, there are various approaches to calculate this. There are the subtractive and there are the additive approaches. So I will slightly elaborate about both of them. So in the additive schemes, what we do, the overall energy is we first calculate the energy of the QM part. We then calculate the environment using molecular mechanics. And then what we have to take care of is the interaction between the QM and the MM, and that's another term that we add into this overall energy in order to get the QMMM energy. There are also the subtractive QMMM methods. In these methods, however, what we do is to calculate the whole system using molecular mechanics, then to calculate the reactive part using molecular mechanics and subtract it from the overall calculation, and then to add to it the same small system, reactive system, using quantum mechanics. So these are two different approaches. Actually, the most common approach is the additive approach, and I will continue to talk about this approach because it's usually more accurate. Okay, so QM, what do we do in the QM? Actually, we solve the Schrödinger equation, and we get the energy, we get the wave function, and now in order to use that, we can use various approaches. So there is the ab initio approach, there are DFT approaches, there are semi-empirical approaches, and pay attention, there is also an empirical approach, which I will slightly elaborate about later. Okay, what about molecular mechanics? So molecular mechanics, we've seen Michael Levitt have shown us very nicely all the different terms, so I don't need to really explain them. So this is how we calculate the QM, this is how we calculate the MM, and now what about the coupling terms? So as I said, we calculate the reactive part using QM, the environment using MM, and now we need to take care of the coupling between them. Now, what is this coupling? What does it account for? So it accounts for electrostatic interaction between the reactive part and the environment. It accounts for bonding interactions. If we actually trim the, for example, if I want to describe this molecule, but I have to cut it somewhere, part of it belongs to the enzyme and part of it belongs to the reactive part. I do have to cut it somewhere. So these are bonding interactions that I have to take care of. And then there are the van der Waals interactions. So let's start. The electrostatic interactions. There are various levels of calculations to account for the electrostatic interactions. The lowest level is the mechanical embedding. In this level, we actually translate the quantum wave function into point charges, and then we calculate the electrostatic interaction between the point charges of the QM part or the reactive part and the electrostatic interaction and the point charges of the environment classically. So this is very easy to calculate. On the other hand, we don't get polarization of the wave function due to the environment. So it lacks something. Then there is the electrostatic embedding, where we take the point charges of the environment and we introduce it into the Hamiltonian of the QM part. So actually the wave function, while it is being calculated in the QM calculation, it considers the environment, and then it knows about the environment, it is affected by the environment, it gets polarized. This is the most common level of calculation. And then there's an even more advanced level of calculation, which takes the polarization of the reactive part on the environment. That's less common usually. It's just part of the environment.
About the dielectric constant?
Yeah. Water in terms of polarization, electrostatic?
Sorry?
Water enters at which level?
It enters, okay, if it is part of the reaction, it enters into the QM part. If it is just the solvent, so it enters into the MM part. And then there is, of course, and then there is the interaction between the rest of the protein and the water with the reactive part. So everything here, you see, these are as if water, these are protein. All of this is considered MM. It's calculated using MM. But then the interaction between this part and let's say this is, for example, a GTP. So this part of the GTP is considered, for example, the reactive part because we want to see the hydrolysis. Okay, so this water molecule will be calculated using QM. This part of the GTP will be calculated as also QM. And then the interactions between this part and these water molecules or this part of the protein, these will be calculated using this depending on the level that we choose. So the most common level of calculation nowadays is this one, the second one, which is it's electrostatic embedding because it allows the environment to affect the polarization of the wave function, to affect the wave function.
So if a water molecule comes in a specific distance to the active site, then it is treated as a catalytic one as well? How you distinguish between water molecule which is not reacting one and the rest?
No,
and
so
the reacting one.
So you know, it depends. If you know more or less what is the mechanism, so you can choose, okay, this water molecule is inside or this water molecule is
so
not
it's
inside.
Not the distance or the location?
It's
because they are dynamics.
It is a
dynamically move.
wait, but we do let. Usually, you do while we. I did not discuss it, but of course we do dynamics and we let the system propagate. So it is a matter of distance in the initial choice, right? Which water I will choose as my, for example, here. So in this system, hydrolysis of GTP, I had to have one water molecule at least inside. Right now, you are right, which water to choose. I could choose, I wouldn't choose this one because it doesn't make sense.
No problem, you choose the one that is the closest one.
Right.
But then
if so sometimes if you really don't trust your results, you can add additional water molecules from the environment and see if it affects the results or if it affects the mechanism.
About water molecules coming in and out.
Yes.
Of your MM part.
They all the time come.
So you sample different configurations, you do dynamics.
Coming in and out where? No, it's all the time moving around. But whatever was chosen to begin with as MM is staying in MM all through the calculation. Whatever was chosen as QM will stay QM throughout the whole calculation. So if that's why I'm saying we increase the size of the QM part in order to see that it is stable, that the results are stable.
So the QM that you are actually doing is a time-dependent QM. You are not looking for energy. You are looking really for time-dependent QM problems. It's not Schrödinger equations with the eigenstate or eigenvalues. You are really looking at the time development of the Schrödinger equation, right?
Okay, we are doing dynamics eventually, if that's what you mean. We are solving the
dynamics of the quantum mechanical form, aren't you? How do you treat
so it depends on the okay, just a minute. No, so there are many different QMMM methods, okay? There are such that are doing what you are saying, there are such that are not doing. There are many different types. All the possibilities are available. There are possibilities it depends. There are some that are, because QM is, as I said, it's very, very costly. So sometimes we do dynamics on one surface and we take the configurations and just as sampling, and we use only later on we use it as single point, for single point QMM calculations, where in that case it's not really time dependent. It's just single points. It depends on what do we do and how do we do. Okay, there are all the variations you can say. Okay. So that was electrostatic, various different levels. Now, what about the bonding? So for the bonding, there are also various different levels. So again, let's try to understand what happens here. The part of the reactive part, some of the molecule is in the reactive part, and some of it is in the is considered as the environment, and we have to trim it somewhere. We have to suddenly cut a bond where some of the molecule is here and some of the molecule is here, and of course it's something here is wrong. So here too we have three different or various different classes. I mentioned here three. One class is the link atom. So we cannot actually take this and calculate in QM because it's just a molecule that lacks something. So usually what you do is, for example, to add hydrogen instead of this missing atom, and then to try to fix for it or correct for it. A different method is the boundary atom, where you don't add a hydrogen, but you try to parameterize it and add something which is more similar to what you have just trimmed. And there are also localized orbitals, where you fix some orbitals and you let them be here. All of these different methods are in order to try to take care of this problem of trimming a bond in the middle and considering some of the system in a QM and some of the system in MM. Okay, and finally there is the van der Waals interactions. These are just considered classically. There is no other way to consider them right now. Okay, so these are, as I said, there are various methods, many different methods in QMMM where the QM part is changing, and I will, in my lecture, I will talk about the special case where the QM part is based on valence bond. So what is valence bond? In valence bond, we actually localize the electrons. We unlike, for example, molecular orbitals or density functional, where the electrons are spread all over the molecule, in valence bond we actually know where the electrons are. And so the advantage of such such method is that, first of all, you can build QMMM approach method. This is what Aryeh Warshel has done. You can build a QMMM approach which is solely empirical. It's completely empirical, which means that it does not use real quantum calculations, but it uses only force fields. And that, of course, makes the method very, very cheap to calculate. Another thing that it provides is the chemical insight, which I will also try to show you later on. So in order to explain that method, I will take a hypothetical reaction. This reaction, AB plus C minus becomes A minus and BC. So it's an SN2 reaction. And in the simplistic valence bond description of this system, we will have two different valence bond states. One state is where A and B are bonded and C has its own electrons. And I will call it the reaction state, the reactant state. And then we have another state where A has its own electrons and B is bonded to C. This we will refer to as the valence, the product state. Now, according to quantum mechanics, the overall wave function is a linear combination of these two states. Okay. Now, what we do, we actually want to look what happens or how does each one of these states behaves along the reaction coordinate. So this is the reaction coordinate. B approaches C and gets away from A. Now, if we look at the reactant wave function or reactant state, valence bond state. So when we go along the reaction coordinate, what happens is that we lose the AB bond. B is getting closer to C. We have a 3-electron repulsion, and therefore the energy goes up. The same, but exactly opposite, happens with the product state. So here we started here where B was very far from C, and that's why the energy was very high. And as we get B closer to C, they get bonded and more stable in energy. Now, according to QM, we know we have to mix these two states, and as a result of the mixing, we actually get, in this case, the ground state, which is the reaction profile of that reaction. So Aryeh Warshel, knowing this, thought about it, that actually each one of these states can be described using force field. It's using molecular mechanics. You actually don't need, for each one of these states separately, you don't need any quantum mechanics. So you can actually calculate each one of these states separately using molecular mechanics. Now, what is the problem? First of all, there is the issue of the fact that at equilibrium, both of them will be zero. So there's no meaning, because it's molecular mechanics, so there's no meaning, there's no physical meaning to the relative energies of these two states. So what does he do? He adds a parameter which makes which brings one state relative to the other to predict the correct delta G of the reaction. So we know what's the experimental. We predict it by shifting one state relative to the other. Another thing is, now what's missing? We are missing the mixing term, right? But we don't have a wave function. So how can we mix them? So here too, he came up with the idea, okay, let's assume that these two states are orthogonal. And then if they are orthogonal, we can mix them by knowing what would the barrier be. So actually the mixing term is this resonance energy. It should be exactly the value that brings me to the correct barrier. So we parameterize, or we calibrate the system in order to fit the experimental barrier and in order to fit the correct delta G of the reaction. So that's the idea, and that's what is done in that method. That's called the empirical valence bond. But just a minute. So far, we've done parameterization, we've done calibration. So, of course, we got a nice profile, but what can I learn from it, right? I mean, it has no value because everything is based on calibration. So no, the idea is that we use the same parameter, that these parameters are intrinsic to the reaction and they don't change with different environments. So we can actually study or parameterize and calibrate the system, for example, in solution, and then use the same parameters and move to the protein. Now we move to the protein, we use the same resonance energy, we use the same gas phase shift, and however, because it's a different environment and the system knows it's a different, the interactions are different, then we will get a different profile, and now we can actually study on that profile. So that's the idea of that method, and it's actually very, very powerful method because it allows us to do one of the major problems, as we heard today from Tamar, is the sampling problem. Now, imagine, you are saying in molecular mechanics is a serious problem. Imagine in QMMM. In QMMM, it's a much more serious problem because each QM calculation can take long time compared to MM. So this is a very powerful method because it is very, very fast. Okay. So now, in principle, just to let you know that these two states can be, as in the EVB, calculated as two independent classical states. And but alternatively, we can also calculate it using ab initio valence bond, and that allows us to calculate more than two states in a relatively easy way. And then we can also use this as a reference potential. So that's something we have developed in my group, but I'm not going to elaborate about it. Okay, so this is more or less what I'm going to say about the QMMM, and now let's try to see some application. So I'll try to walk through with you on some two small examples to try to see, first of all, how or what kind of insight we can get from this kind of calculation, and to see that how can we understand reaction mechanisms within enzymes.
Does it work well with simple reaction, oxidoreduction of simple molecules?
Sorry?
Does it work well with simple oxidoreduction, for example, of molecules? If you take a simple molecule for which you don't have this problem of computing parameters, does it work well to predict the reactivity, for example?
Yes, I mean, it depends. What do you want? Okay, again, this method,
No, no.
I don't know what are you talking about. If you're talking about the EVB, so the EVB is a comparative kind of study. You always have to study the system in one, the reaction in one system, where you do all the parameterization and the fitting and the calibration, and then you move to another system where you don't touch anymore the fitting and the parameters and the calibration, but you can get the results. Yes, this works well. Now, what did you ask? This?
If it has been tested in a simple chemical reaction where you look at an oxidoreduction, for example, of two simple molecules, and you change the pH, you change whatever temperature, whatever, and the question is whether the reactivity predicted by this approach indeed fits very well.
What do you call this approach? Which approach?
The empirical valence bond theory that you just
Again, so you have, what do you call simple molecules? Because two molecules in gas phase is okay, going to be my reference. No, it's going to be, let me explain. It's going to be my reference reaction. And then if you want, you can study it in gas phase, yes, and then move to solution. Yes, it works very well. Of course, it depends on the parameterization, calibration, it depends on the person who was doing it, right? No, because
you have measurements. You can have measurements in a gas phase from which you are going to extract the empirical parameters,
right,
and then apply those parameters in the liquid phase.
right, yeah. So it works very well. If you do it properly, it works very well. But the parameterization is a lot of work. This is the drawback of that method. The parameterization is a lot of work. But once you did it, and if you have enough experimental data to compare so that your parameters are good, then it's a very good method. Okay, so so we know enzymes are very complex systems, and part of the complexity is that there are many, many residues, and we actually don't know what is the role of each one of them. And it would be nice to be able to understand what is the role of each one of them. For example, in this system, if this is my reactive part, what would be the role, for example, of these random residues that I was picking here? Now, recently, various researchers have shown that if electrostatic has a major role in catalysis, then it is possible to identify what we call hot spots. And what I will try to show is that using valence bond, we can provide additional insight into these hot spots idea. So this is the system that I will focus on. So it's a haloalkane dehalogenase family, and I will focus on two different enzymes, the DHLA and the DHAA31, which is a man-made mutant of enzyme in that family. Now, this enzyme, this family of enzyme converts haloalkanes, which are very toxic, into alcohols, and that's why it would be nice to have more of them. Okay, the reaction that I will focus is the first step in that reaction, which is an SN2 reaction, and in the first enzyme, which is the DHLA, I will focus on the model system of methyl chloride with the enzyme where the aspartate attacks the methyl chloride and replaces the chlorine. So this is an SN2 reaction. Now, what we've done here is we were using combination of what I call VBMM, which is ab initio valence bond combined with MM, with sampling taken from EVB. So this is what we've done here. And here I'm showing some results of the anti-catalytic effects of various known mutants. So here we have results from FEP, from free energy perturbation approach. And these are the observed results. And we can see, I mean, all the mutants are supposed to be anti-catalytic, and indeed we are succeeding to get the anti-catalytic effect. You know, the values are not identical, but it's good enough. I mean, it's hard to expect much more than that. Here we have the results using an approach which we call LRA, linear response approximation. And we can see that here too the results are relatively in good agreement. And that's actually very nice, because one property of the LRA, or one advantage of the LRA, is that it is additive. So if LRA is working, first of all, it means that electrostatic has a major role in catalysis, because it's based only on electrostatic contributions. And second is that we can use the additivity of the LRA, which is, in a second I will show you why is it nice. Sure.
So this is including this hotspot that you're talking about?
I will get to the hotspot. So now,
the epsilon is the effective the electron constant equal to?
yes.
You always use epsilon equal to?
No. We
Optimize it?
just like any other parameter in the EVB, this is another parameter that is being,
But within a range,
of course, within a range. I mean, you know, you don't go more than 80, right? Because no. So yeah, within a range, you know, no, you don't go below 1. Yeah, I mean, there's no, I know systems that people have been using 10 and sometimes 20. It depends. If you sometimes for ionizable residues you use more. No, so sometimes you use different dielectric for. No, it depends on the system. Again, I cannot. But sometimes you use for ionizable residues a larger dielectric constant than for non-ionizable residues, because they lack much more, you know, many more effects are missing there. It's more difficult to describe them correctly, so you are using that to help the system to reach the correct results.
The correct result is judged by comparison to experiment?
Experiment. Always do experiment.
Do you parameterize this E for each residue separately?
No. We parameterize it per system, I will say. I'm just saying that it happened. I know papers that used for a certain distance from the center one dielectric, and for a farther distant a different dielectric. But it's not very common. Usually, if you use the dielectric, you use only one for the whole system. But it's per system.
The units in the table are KT?
Sorry?
The units in the table are KT?
Yes. kcal. Kcal.
Is a physics.
Yeah. Kilocalories, sorry. Yeah, I should have put them. Okay. Okay, so just to slightly understand what have we been doing. So what we've been doing in the using the LRA, we were actually calculating the solvation energy. So what do we do in the LRA? Unlike the FEP, what we do here is we calculate the reaction in the gas phase, and then we calculate the solvation at only 2 points, at the reactant state and in the transition state. And then from the difference, we can estimate how much has the barrier changed. Yes, and that's how we estimate the barrier in the protein. So in the reactant state, there are certain interactions, and based on these interactions, we can actually calculate the solvation in the reactants. When we move to the transition state, the charge that was localized on the aspartate now is completely delocalized. We have different interactions with the enzyme, and that's why we have also different solvation energy. And eventually, what we do is the difference between these two solvation energies is actually what we call delta delta G of solvation. And if it is positive, it means that it is increasing the barrier. If it is negative, it means it's reducing the barrier. Now, quantum chemistry, right? Yes, of course. No, it's a QMMM method. So the reactive part is always using quantum calculations. Here I was using potential of mean force with umbrella sampling for the FEP, not for the LRA. I didn't get into these. I can, okay. Okay, so positive is increasing the barrier, negative is reducing the barrier. And now, what do we, so as I said, we have the advantage of the LRA being additive. So if we can calculate it for the whole protein, we can calculate it also for each residue separately. So this was calculated for the whole protein. Now we will do the same thing, but we will look only on the contribution of each residue. And that's how we actually get those hot spots, because we can actually get the value, the contribution to this differential solvation energy of each residue separately, and that's how we get those different peaks. So as I said, negative peaks are residues that are reducing the barrier or catalytic, and positive are those that increase the barrier or are being anti-catalytic. If we look here, we can see that, for example, tryptophan 175 is highly catalytic. And actually, it's nice, and also tryptophan 125. And this is actually nice because these two residues are known from experiment to be very catalytic. So, or that mutations of these residues are highly anti-catalytic. So it's actually nice. And but this is something that was known, and we were asking ourselves, can we now try to understand why this residue is catalytic? So here we are looking at tryptophan 175, and we see that the contribution of this residue to the solvation is stabilizing both the reactants and the transition state, but it is stabilizing the transition state more than the reactant. That's why it's catalytic. The question is, can we understand, again, I'm saying, can we understand why? And here comes the use of the valence bond. So just like we were able to decompose the total contribution into the contributions of different residues, we can further decompose it into the contributions of different valence bond structures. So let me show what are the different valence bond structures in this system. Oops. So this is the reaction, and the various valence bond structures that we took into account were these ones. So here we have the carboxylate and a covalent bond between CH3 and Cl. Here we have covalent bond here and negative chlorine. Here we have carboxylate ion, positive methyl and negative chlorine. And here we have what we call the long bond. So these are relatively important valence bond structures in this type of calculation. And now, as I said, the wave function is a linear combination of all these different states. And now we can take what we got here and look at decompose it even further into the contribution of the valence bond structures.
The overlap integral is just one number? It does not depend on reaction?
Sorry?
The overlap integral.
Yeah.
Those various wave functions.
No,
Just
so
one number will depend also on
no. So now, okay, so we have to separate the VBMM, which is ab initio valence bond, and there you have overlap. Each one is different. I mean, the overlap is different between different states. and everything is calculated, and the EVB. In the EVB, you don't have overlap. You assume that the states are orthogonal. In the VBMM, we consider the overlap, we consider everything. And yes, I didn't show it, but this is actually based on some approximation that we can decompose it based on the weights of each valence bond structure, based on the weights. It's okay, so these are the different valence bond structures that I've shown, and what we see is that this catalytic contribution comes mainly from here and from here, from these two valence bond structures. Now if we look what is common to these two valence bond structures, we can see that both of them share the chlorine atom, chlorine ion, and indeed we know that this tryptophan is actually catalytic because it stabilizes the leaving chlorine in this reaction. Now, we know that from experiment, but the computer didn't know that when it did the calculation. So we actually got, explanation of what is the role of this residue just based on the calculations. Another example is here we see two glutamates, and one of them is here, 56 in the hotspot. It looks anti-catalytic, whereas the other one, 293, looks catalytic. And the question is, can we try to use our method and explain why? Why is it catalytic? One of them is both of them are the same residue. Why one of them is catalytic and the other one is anti-catalytic? So first, we are looking at the overall solvation, and we can see that in both cases, both residues destabilize the system. So they are not stabilizing, but they cause destabilization. But in glutamate 56, the destabilization is higher in the transition state, and that's why overall we have an anti-catalytic effect. Whereas in 293, the destabilization is higher in the reactant state, and that's why we get a catalytic effect. So we further decomposed it, and what we could see is that in the case of glutamate 56, the interaction is with these two valence bond structures, and if we look at these two valence bond structures, again, what's common is the chlorine ion, which means that the interaction is destabilizing with this chlorine ion. And that's why it is anti-catalytic. On the other hand, in the case of 293, the dominant effect, or the reason why this is catalytic comes mainly from the interaction with the covalent of the reactants. And if we look at on that structure, we see that the negative charge is now on the carboxylate. So actually, we understand that in this case, this residue interacts more with the carboxylate, and that's why eventually, because it's in the reactant, that's why it's destabilizing the reactant, that's why eventually it's catalytic. So using this, we actually can understand what is the role of each residue in catalysis. Now here we try to see what happens if we mutate. What happens? So these are changes in the contribution of the differential solvation due to mutation. So here we looked at the tryptophan to tyrosine mutation, and what we can see is that the major difference, or the major change, is actually in the position of in position 175 itself, in the mutation itself. So first of all, what we can learn from it is that the mutation did not cause any serious structural changes in that protein, and when there are no serious structural changes in the protein, we can actually continue to look at the effect of this particular mutation in order to understand how the mutation is going to affect the catalysis. And indeed, if we look here now, so if we remember before, so tryptophan 175 was catalytic, and mainly because of interactions with these two chlorine ions. So when we mutate it to this tyrosine and we do the same analysis, we can see that, again, it is catalytic, but much less catalytic. And if we look at the reason for catalysis, so we see that it comes from the same dominant structures, dominant valence bond structures. And indeed, losing this hydrogen bond, so we actually can understand why we got less catalytic effect now. Okay, so in general, we did various mutations, and we've seen that always when structural changes of the protein are not large, so the same dominant valence bond structures that were in the native will also be important in the mutant, and that's actually nice because.
So did you try to do the mutation not just in the computer but also?
No, these are known mutations. These are known mutations that we only try to study and see if we can understand.
Okay.
So this is.
So they were shown to be active.
Yes. Inactive. They reduce the catalysis.
Reduce, but
yes.
inactive,
yes.
right?
Yes, these are all known mutations. So far, I did not.
Okay.
Yeah. So as you say, so can we do predictions? Yeah, that's exactly the question, and we think that yes, in cases where structural changes are not going to be, I mean, the mutation is not going to cause big structural changes, and this is the glutamate 56 that we have seen before, and we have seen before that it was anti-catalytic, and it was anti-catalytic mainly because of interactions with these two chlorines. So what we were thinking is that, okay, if we can actually take and change this anti-catalytic effect to less anti-catalytic effect, or maybe instead of anti-catalytic to become stabilizing instead of destabilizing, then maybe we can get catalysis. And indeed, we did this mutation of glutamate to glutamine. So structurally, it's a very small change, and we don't expect it to affect the whole structure of the protein. On the other hand, instead of instead of destabilization, now we got stabilization. And what we've seen is that the effect of this residue was turned from anti-catalytic to catalytic. We calculated the whole protein, and indeed, in this case, our calculations based on FEP and based on LRA are predicting that it will be catalytic. Now we turn to the experimentalists. What's the problem? They're not interested in this particular system. They were interested in a much, larger system, and that's what brings me to the. So it's that's why we moved from the first haloalkane dehalogenase to a different one, this man-made mutant, and what they succeeded to do, the group of Domborski has succeeded to create a synthetic pathway for biodegradation of 3-chloropropane, this TCP, which is a highly toxic molecule. Now, the problem is that throughout this biodegradation, the first, okay, so let me start by, this molecule is pro-chiral. So, before the reaction, it is not chiral at all, but once you do a SN2 reaction, it becomes chiral. So this one is already chiral. Now, the first step in the in this pathway is non-selective, but the second step is R-selective. And the problem is that you get accumulation. If you don't make this selective, you will get accumulation of the S product. And that's not good, because you want to get rid of the whole thing. So our role here was to see whether we can try to make this more enantioselective. So this is the objective, and again, the SN2 reaction, the first step, is the one that dictates whether this is going to be R or S, and that's why it's important to study that step. And okay, so here is the mechanism that we have solved. So here is another example. First, we've shown you some insight that we can get. Now I'm showing some solving of a mechanism. So this is the substrate, and this is the aspartate. And now there are two positions where where aspartate can attack. It can either attack here or attack here. Now, if it attacks here, then we will get a R product. Whereas if we attack here, we get the S product. Now, calculating the barrier, we have seen that the R product in this case is much more stable. And we could actually explain it because in this case, when we attack here, the chlorine is leaving close to the halide stabilizing part of the enzyme, and that's why it is being stabilized and makes the barrier lower. Whereas where if we attack here, the chlorine is left in the hydrophobic cavity, and that's why it's less stable. And on the other hand, we could actually, just a minute, we could actually have a different orientation of the TCP itself. Now in this orientation, after it rotated, now we get exactly the opposite. So now attacking here would give us the S product, which is going to be more stable, and attacking here would give us the R product, which is less stable. So first of all, just based on this, we are currently trying to find some residues that would hinder this orientation and would allow only this orientation to stay inside the protein, or to prefer this orientation, because then we will get the R product in preference. Otherwise, we have done the calculations of the barriers, as I said, but we have some problems. Now, what are the problems? So first of all, these are the observed barriers, and we can see that our barriers, both LRA and FEP, are much higher in both cases. In addition, we can see that whereas, experimentally the barrier for both, or the rate for both the R and the S are supposed to be identical, our results are showing a slight preference for the R. So there are some problems with the calculations, and as I said, this is a man-made mutant, and we could, it's very, we could see the big difference between calculating this enzyme and calculating the previous enzyme, which was a native one. There's a big difference because this one is very unstable. So we are now getting a new enzyme which is more stable, and trying to work on it. Yeah, okay, I think I will skip this. And I've got some marks. And okay, so I've shown you some what are QMMM approaches. I think I've shown you concentrated on the valence bond based approaches and try to explain the insight that we can get, and that's it. Okay, so I would like to thank my group members, and in particular Avital Shurki, who is sitting here in the audience, and Raja Pandyan that did the project that I was talking about. And thank you for your attention.
Questions?
Is it possible to use this method to analyze long-range interactions?
Like what? Yeah.
Well, let's say, for example, you have a transmembrane protein and you have a ligand binding on the other side. You have a allosteric effect, and can you detect this long-range interaction?
Okay. What do you call this method? This method is exactly like any other molecular mechanics method. It only has you know, for a certain part that you think that needs more accuracy or needs where you need to take into account some quantum effects that you cannot describe using some, you know, molecular mechanics, then you need to use that method. You understand? So I'm not sure what kind of long-range interactions you're talking about, but in principle...
Allosteric reactions, for example.
Sorry?
Allosteric changes, for example. Can you model these kind of things?
Yes, so allosteric, but for what? If it is just an allosteric for some binding of two proteins, I'm not sure I would use this method because the QM makes it so much slower and so much more computationally expensive that, and I'm not sure it's necessary for just, let's say, two proteins that are binding. But if you have a reaction that happens there, or if you have some, you know, electron transfer or things that require quantum effects, then you can, and yes, and depending on how much sampling you do, you can also account for the, it depends on the sampling. It's exactly the same problems that you encounter in the molecular mechanics calculations.
I think he's asking, I'm not sure, I think he's asking, you're binding at one spot and you affect the environment. So in principle you can do it.
No, of course you can do it, but...
Yeah, but you have to change the environment and do a different calculation.
Yes, but binding of what to what? Sometimes it's not worth it. If there are no quantum effects, it's not worth it to go into the QM, you know, calculations.
If bonds are made.
If there, yes, so what's the point? You understand? That's what I'm trying to understand.
The previous lecture, you did how it works is that you have binding of nucleon on one side and this causes some long range static changes. So can you
Right, but
can I use your protocols for the purpose of designing novel enzymes? Like if I have some specific reaction to target, and if I can find some specific scaffold which can accommodate that transition state for that reaction, can I design the surrounding residues, maybe, and
I mean, in principle, that's what eventually we have been trying to do, but with at least in the, you know, so far not with so much success, but this is what we are trying to do.
Okay.
First of all, I would like to thank you for you answering the questions we asked. For the patience, thank you. Second, yeah, because we asked a lot of questions. I think the problem some professors has talked about the QM-MM definition of the QM sphere, the definition of how you define the QM region and MM region and the water dynamics. Is that the water gets in and out of the, which is created and annihilated
Look,
within
we
that
are,
region?
we are, it's not single calculation, we do dynamics. We, you know, so everything that happens in whatever you know from molecular mechanics happens here as well. So if a water, it's just, you know, once I chose that one water molecule belongs to, is being calculated using molecular mechanics, it will stay calculated molecular mechanics, but it can move anywhere. The decision of what is, you know, it's in the painting, it looks like this area is QM. It's not this area, it's these atoms, okay? It's these molecules. These molecules can move, they can move somewhere else, and that's okay.
So it is not defined by a volume of QM?
No, it's not defined by volume, it's defined by atoms. Which you know, you tell the program, this and this atoms or molecules are going to be considered always using quantum calculations. These and these atoms are going to be considered only molecular mechanics. Now, if they have to move and they even switch, you know, the water goes very far from, it can happen. No problem. Okay?
Okay, thank you.
Maybe I should have shown some movie of a reaction, so then it would have been more clear. I didn't.
Two questions. The third questions, does the EVB results fit with some other maybe semi-empirical models and that described atomic orbitals? I don't know, like STO model, basis set or something like that?
The EVB is not trying to, has nothing to do with orbitals.
No, I'm
That's
just trying to ask how these results fit with some calculations of other
yes,
models.
of course, of course.
And the second one, do you time propagate it and like extract some, I don't know, like chemical rates or kinetic rates for how long does it take for the reaction to happen?
So, you know, once you have the barrier, you can translate it into the kinetic parameters, right? You can convert the barrier into the kinetic parameters.
Okay. So
We don't
basically
usually
you
do
can
real time.
basically
We
do
don't-
it you can predict it or you have to calibrate it with measurements.
No, we try to predict it.
All right.
Again, I don't know which method you are talking about because each method
No,
is
the EVB,
different.
the EVB.
Yes, so in the EVB, you calibrate it only on one system, either gas phase, usually not gas phase, usually solution, because usually you try, because, you know, it is sort of approximation that the parameters do not change. So usually you try to have a similar system to the protein one. So solution is more similar than gas phase usually to the protein one. It's more, you know, there's more electrostatics, it's more, so you usually calibrate it only on the solution system, and then when you transfer to the protein, you don't calibrate anymore anything, so it's just predictions. Over there it becomes predictions.
You said that you can look at the different amino acids and their contribution to the catalysis or decontribution, the
Right.
repelling of the catalysis. Can you distinguish between catalysis and binding, or if I will talk in terms of Michaelis-Menten, between catalysis per se or between Km and Kcat? Because at the end of the road, both will decrease the activity of the enzyme.
Yes, no, of course. So what we have been doing here is we were looking only on the Kcat, like on the effect of the Kcat, not on the effect of the Km.
But
if you want,
if you look at all many different residues, their contribution. So
but we are looking at the contribution to the barrier, which is what dictates the Kcat. We look at the barrier that goes from reactants, or the complex, the reactant complex. We don't start from outside of the protein. We start from the complex.
So it's already, so the
It's already,
initiation
yes.
is already
Inside, yes.
or in the active
Right,
side.
right.
I see. So you cannot look at the...
It's not that you cannot, you can, but it's a different story. It's not what we've been doing.
So the last question.
First of all, thank you very much for your patience and your pedagogical talk. I have I have a further question. You talk about reaction. There is lots of work on fluorescent proteins, and in particular protein that will be fluorescent upon voltage change. Can you apply your approach to predict how isomerization of a fluorophore, for example, could induce? Can you predict the fluorescent properties of proteins using the approach?
Fluorescence.
Yes.
Yes, in principle, yes. I have not been doing it, but I have here. We have here Igor, who probably is going to do a lot of it very soon. Yes, it's as I said. I mean, I was focusing only on reactivity, but as I said, every property that can be calculated within QM can be calculated within QMMM, because it's just okay. You have to, in QMMM, you do QM calculation, and you just include also the effect of a larger system. So the environment is calculated at a lower level, the MM, but it is still, you know, every property that QM can give, you can get also in the QMMM.
So to modify the fluorescent properties of various proteins, or is it done only empirically?
Sorry?
Has your approach been used in order to modify fluorescent protein to achieve certain wavelength or whatever?
To modify. No, as I said, it's
posterior
exactly his
It's-
project, what he plans to do
I
soon.
think it's still, you know, the area of active research. It's still
What?
still one of the challenges what you asked.
Yes.
Okay, let's thank the speaker for a beautiful lecture.